Welcome Geniuses, I'm Genie, your best buddy for A-levels. In this channel, we'll bring you to explore the secret formula behind success.
Now, let us look at the steps to follow in solving simultaneous linear equations in three unknowns. So the first one is write down the equations in augmented matrix form. The second one is use the elementary row operations to reduce the augmented matrix to echelon form. So have a look at this example. So this is on the left, the original augmented matrix form, and on the right, the echelon form. So, for the third step, we are going to determine whether or not the solutions to the equations exist. So we are going to ask ourselves, are the equations consistent? And in the fourth step, we are going to identify the geometric significance of the planes, represented by the original system of equations, if it is required by the question. And the last step is, if there are solutions, proceed to find the solutions as follows. So the first one is, you want to determine the number of independent equations. So identified by counting the number of non-zero rows in the coefficient matrix. And the second step, we want to calculate the number of free variables, which is the number of unknowns minus the number of independent equations. And the third step, we want to identify the leading variables and deduce the identity of the free variables. And the fourth step is to express each unknown in terms of the free variables. And the last step is to write the solution in the form of a vector with the bracket x, y, z vertically. Okay, let us take a look at this example. We want to find the set of solutions to the system of equations given below. So x minus y plus 4z equals to 3, 2x plus 5y plus 3z equals to 4, and 9x plus 19y plus 16z equals to 19. So we are going to put this into a matrix form. So writing the system of equations in the form of an augmented matrix and performing the row operations leads to the working shown here. So we have the first one, row 2 minus 2 times row 1 for the new second row. And then for the new third row, we have the old matrix third row minus 9 times row 1. For the second step, the new third row is the previous matrix third row minus 4 times the second row. We can deduce from the final matrix that the original system of equation is equivalent to two independent equations in three unknowns, and that since there are no rows of the form of 0, 0, 0x, where x is not 0, then the equations are consistent. Since it is clear from the original equations that no pair of rows in the coefficient matrix is a multiple of each other, we can conclude that no two of the planes represented by the equations are parallel. Therefore, the planes form a sheaf, and the set of solutions to the equation is a straight line, r equals to a plus lambda b. Since there are two equations in three unknowns, there is one free variables. In other words, one of the variables has to be assigned an arbitrary value in order to find the set of solutions to the given system of equations. The free variable is z, so we set z equals to lambda. The free variable is chosen by making use of the rule never choose a leading variable as a free variable. Leading variables are those which are linked to the first non-zero coefficients in the rows of the final matrix. This matrix is repeated immediately below. The first non-zero coefficients in the rows of the final matrix are ringed or circled. We deduce that x and y are the leading variables. This leaves only z to be chosen as the free variable. With z equals to lambda, we can deduce that the final matrix represents the following equations: x minus y plus 4 lambda equals to 3, 7y minus 5 lambda equals to minus 2, and solving these equations for x and y in terms of lambda gives x equals to 19 over 7 minus 23 over 7 lambda, and y equals to minus 2 over 7 plus 5 over 7 lambda. And now we are going to represent it in a vector form, r equals to a plus lambda b. However, note that the direction vector b can be multiplied through by any suitable non-zero values in order to make the elements of b all integer. So, multiplying through by negative 7 will gives b equals to 23 minus 5 and negative 7. So, the set of solutions now becomes this. Let us now look at how to change the basis vector. So far we have established that if a set of n times 1 vector is a basis for Rn, then any vector can be expressed as a linear combination of these vectors. The cases n equals to 2 and n equals to 3 are described in more detail below. So let us take a look when n equals to 2 first. So the standard basis E for R2 is given by 1, 0 and 0, 1. An alternative basis F for R2 is 3, negative 4 and 1, negative 1, for example. The vector 1, 2 with respect to the standard basis is written as 1, 2. Note that 1, 2 equals to 1 times the 1, 0 vector and 2 times the 0, 1 vector, which is a linear combination of the standard basis vectors 1, 0 and 0, 1. Since an alternative basis f for R2 is 3, negative 4 and 1, minus 1, it must be possible to express 1, 2 as a linear combination of the basis vector 3, negative 4 and 1, negative 1. Thus, 1, 2 equals to alpha times 3, negative 4 plus beta times 1, negative 1. Or you can rewrite it in terms of matrix form, which is like that. Pre-multiplying both sides of this equation by the inverse of 3, negative 4, 1, and minus 1, and rearranging yields alpha beta equals to negative 1, 4, negative 1, 3, which is the inverse of the previous matrix, times 1, 2, and you obtain negative 3 and 10. Thus 1, 2 with respect to the standard basis E is equivalent to negative 3, 10 with respect to the new basis F. This relationship can be written more concisely as 1, 2 with small little e is equivalent to negative 3, 10 with a small little f. Note that 1, 2 equals to negative 3 times 3, negative 4 plus 10 times 1, negative 1, which is a linear combination of the basis vector forming the new basis. If we form a 2 by 2 matrix P, which has columns which correspond to the new basis vectors in corresponding order, then P equals to 3, negative 4, 1, negative 1. Noting that 1, 2 can be written as a linear combination of the columns of P. We deduce that 1, 2 equals to 3, negative 4, 1, negative 1 matrix times negative 3, 10. We deduce that the equation connecting a vector in the standard basis referred to as the old basis to the equivalent vector in the new basis is given by x old equals to p times x new, where for example x old here is 1, 2 and x new here is negative 3, 10. When n equals to 3, the standard basis E for R3 is given by 1, 0, 0, 0, 1, 0, and 0, 0, 1. An alternative basis F for R3 is 1, 2, 3, 1, 3, 4, and 3, 10, 14, for example. The vector 1, negative 2, 3 with respect to the standard basis is written as the same 1, negative 2, and 3. Note that 1, negative 2, and 3 equals to 1 times 100 plus negative 2 times 010 plus 3 times 001, a linear combination of the standard basis vectors of 100, 010, and 001. Since an alternative basis F for R3 is 1, 2, 3, 1, 3, 4, 3, 10, 14, it is possible to express 1, negative 2, and 3 as a linear combination of the basis vectors 1, 2, 3, 1, 3, 4, and 3, 10, 14. Thus, 1, negative 2, 3 equals to alpha times 1, 2, 3 plus beta times 1, 3, 4 plus gamma times 3, 10, 14. Or you can write it in the matrix form, like this. Pre-multiplying both sides of this equation by the inverse of the matrix and rearranging yields alpha, beta, gamma equals to 2, 2, negative 1, negative 2, 5, negative 1, 1, negative 4, 1, the inverse matrix, times 1, negative 2, and 3, which equals to 9, negative 20, and 4. Thus, 1, negative 2, 3 with respect to the standard basis E is equivalent to 9, negative 20, 4 with respect to the new basis F. This relationship can be written more concisely as 1, negative 2, 3 with a small little e, which is equivalent to 9, negative 20, 4 with a small little f. Note that 1, negative 2, 3 equals to 9 times 1, 2, 3 minus 20 times 1, 3, 4 plus 4 times 3, 10, 14, which is a linear combination of the basis vector forming the new basis. If we form a matrix P which has columns which correspond to the new basis vector in corresponding order, then P equals to 1, 2, 3, 1, 3, 4, and 3, 10, 14. Noting that 1, negative 2, 3 can be written as a linear combination of the columns of P. Once again, we can generalize and deduce that the equation connecting a vector in the old basis to a vector in the new basis is given by xo equals to P times x new, where the columns of P correspond to the basis vector forming the new basis. Now consider a matrix transformation A with respect to the standard O basis, which maps the vector xo to yo. Thus, A xo becomes yo, which can also be written as yo equals to A times xo. If, for example, the matrix transformation A is given by A equals to 6, negative 4, 3, negative 1, it is rather difficult to give a geometric interpretation of the effect of the transformation. We now investigate whether it is possible to find a matrix transformation with respect to a new basis which takes the form of a diagonal matrix. A 2 by 2 diagonal matrix is a matrix which takes the form lambda 1, 0, 0, lambda 2, where all of the elements which are not on the leading diagonal are 0. The leading diagonal consists of elements lambda 1 and lambda 2. These elements may or may not be 0. A 3 by 3 diagonal matrix is a matrix which takes the form lambda 1, 0, 0, 0, lambda 2, 0, 0, 0, lambda 3, where all of the elements which are not on the leading diagonal are 0. The leading diagonal consists of the elements lambda 1, lambda 2, and lambda 3. These elements may or may not be 0. The concept of a diagonal matrix can be extended to an n by n matrix, written as like that. If we denote the desired diagonal matrix transformation with respect to the new basis as D, then we obtain x new being transformed by D to become y new. Thus, y new equals to D times x new. But we know that xo equals to P times x new, and that yo equals to P times y new. Thus, y new equals to the inverse of P times yo. And we know that yo equals to A times xo. And xo equals to P times x new. So y new equals to the inverse of P times A times P times x new. But y new equals to D times x new. Therefore, inverse of P times A times P equals to D. This equation connects the matrix transformation A with respect to the O basis with the equivalent matrix transformation D with respect to the new basis. We now need to find a means of obtaining a new basis for which the matrix transformation D with respect to this new basis is equivalent to the matrix transformation A with respect to the O standard basis, where D is the diagonal matrix. Pre-multiplying both sides of the equation, P negative 1 AP equals to D by P yields AP equals to PD. If we write P equals to x1, x2, x3, in a case where n equals to 3, where x1, x2, and x3 are the columns of P, the equation AP equals to PD can be written as A times x1, x2, x3 equals to x1, x2, x3 times the diagonal matrix, which is lambda 1, 0, 0, 0, lambda 2, 0, and 0, 0, lambda 3. Thus, ax1, ax2, ax3 equals to lambda 1x1, lambda 2x2, lambda 3x3. This is equivalent to the following equations. ax1 equals to lambda 1 times x1, ax2 equals to lambda 2 times x2, and ax3 equals to lambda 3 times x3. Which are equivalent to ax1 equals to lambda 1 times ix1, ax2 equals to lambda 2 times ix2, and ax3 equals to lambda 3 times ix3, where I equals to the identity matrix 1, 0, 0, 0, 1, 0, and 0, 0, 1, which in turn are equivalent to a minus lambda I times xi equals to 0, where xi is not 0 and I is 1, 2, and 3. The generic form of this equation is given by a minus lambda times I times x equals to 0. Since we are seeking for non-zero vectors x which satisfy this generic form, then the modulus of a minus lambda I, or its determinant, equals to 0, and this is known as the characteristic equation. In the case n equals to 3, A is a 3 by 3 matrix, and the characteristic equation will be a cubic polynomial in lambda, with the roots lambda 1, lambda 2, and lambda 3, which are assumed to be real and different. The roots of the characteristic equation are the eigenvalues of the matrix A. For each root, lambda I, there is a corresponding eigenvector, xi. The matrix transformation A, with respect to the standard basis, is thus found to be equivalent to the matrix transformation D, with respect to a new basis, x1, x2, x3. The elements of the leading diagonal of D are the eigenvalues of the matrix A, whilst the columns of the matrix P are the corresponding eigenvectors of the matrix A.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.